grayscale. It can operate at different resolutions. The standard resolution is 640 by 480.
The microcontroller we will use is the Max32 development board from ChipKit. It has a very fast 80 megahertz processor and many different peripherals. It has over 80 pins for digital I/O, I2C, serial communication, output compare, and also timers. We flash it with C code using MPLAB IDE.
All right.
I'm going to let Dwayne take care of the stepper motors.
Thank you. Stepper motor is basically a synchronous motor designed specifically to take discrete steps. It experiences really no wear and tear and is virtually maintenance free. And you can use it in applications like inkjet printers, CNC machines, and volumetric pumps. And there's 4 basic variations of stepper motors. You have a variable reluctance, which moves on the basis of minimum, moving from the highest reluctance to the lowest reluctance when you apply a magnetic field. And then you have a permanent magnet motor, which is basically, it has a rotor and a stator that has a permanent magnet inside of it, and it moves on the basis of repulsion and traction with the magnetic fields in the stator. And we also have a bifiller, which is very identical to a bipolar motor in that it has its windings parallel to each other, and hybrid stepper motor, which is basically a combination of both permanent magnet and variable reluctance stepper motors. And here is basically the different stepper motors. You have the variable reluctance stepper motor that has a common center tab, and we have, these are the permanent magnet motors. They have 2 different variations. You have a unipolar stepper motor and a bipolar stepper motor. The unipolar motor has a center tab, and the bipolar stepper motor does not have the center tab. And the bifiller stepper motor is very similar to the bipolar stepper motor, as you can see. The only thing is that you have these parallelly winded windings. And this is basically how a variable reluctance motor operation works. It moves on the basis of reluctance, which is a function of the rotor's position, and it moves from the lowest reluctance in the teeth path. So you have a north and south pole moving, and a magnetic field moving. And here's a permanent magnet stepper motor, which we use for this project. And this is how this is a diagram showing you how current moves through the coil winding, and it moves kind of like a bar magnet. So it moves on the basis of repulsion and traction. So how do we drive a stepper motor? We basically drive a stepper motor with pulse width modulation. We apply a DC signal from 0 to 5 volts over time. And also we can generate the pulse width modulation by logic circuits to generate the sequence to run the stepper motors. And we also need a driving circuit, which is, this is an example of a permanent magnet driving circuit. It's 2 H bridges. You have 2 NPN transistors and 2 PNP transistors. Here are the PNP and these are the NPNs. And they're connected to a controller, which is the logic circuit that I showed you in the last slide. And you can also, 2 different methods you can do this. You can do this by digital I/O, or you can use the analog circuit, logic circuit. We both use both of these in our project. We use the PIC32 to the I/O pins from there. We can use this as a CMOS quad driver, and we connect it to the windings of the stepper motor. And the results we saw after I spent 10 hours soldering this thing, we were getting, the stepper motor was working, but it would be missing steps because of the code that I was running from the microcontroller. It had to be precisely pulse trains, and if you do the incorrect pulse train, if the stepper motor if you don't wait long enough for the stepper motor to receive the input, it would miss steps, and that's what we were seeing. And then I measured the output waveforms from the output circuit, and I was seeing that it was getting some noise. And the next motor we're going to talk about is the servo motor. It's basically a motor that is widely used in robotics and RC cars. And this is what the servo motor looks like inside. It has, potentiometer control unit, a servo case, a motor, and it basically has a 3-wire configuration. It has an IO pin, it has a VCC, and it has a ground. And to control this servo motor, we basically provide a pulse width modulation signal. You have, from the rising edge to the falling edge, you have a 1.5 millisecond pulse that you use to stop the motor. And it has to be separated by a 20 millisecond pulse train. So the combination would be, the period would be 20 milliseconds plus the 1.5 milliseconds.
So a 21.5 millisecond period. Right. To turn the motor in either direction, you would decrease this pulse width to a minimum of 1.3 milliseconds. To turn it counterclockwise faster, you would increase the pulse width to 1 milliseconds. If you go past 1.7 milliseconds or below 1.3 milliseconds, it doesn't get any faster. Those are the max pulse widths.
And the results we're getting was that this was the motor we want to use for a project because it was easier to control and had a faster response time than the stepper motor. And it basically met the design applications that we wanted for the project.
Okay, the meat of the project was the image processing. We chose MATLAB because it has very high image processing capability, and our goal is to track a subject on video, and MATLAB has those capabilities to grab images and process them in the way that we want. There's many different methods that we can use to do that, and that method that we choose must identify targets very accurately. So MATLAB, like I said, it's a very high-level programming language. There's many different uses and capabilities. The different applications that we can use with MATLAB are divided into libraries called toolboxes. The two main toolboxes we used were the image acquisition and the image processing toolboxes. And we also implement a COM port, or one of the USB ports on the laptop, to use serial communication between the laptop and the Max32 development board. Images and video in MATLAB. Pictures are essentially large matrices of pixels. If we have a picture of 640 by 480 resolution, that's essentially 640 columns by 480 rows. So if we multiply those two numbers together, we get 307,200 total pixels. Videos consist of many pictures or frames. So 60 FPS is essentially 60 frames or 60 images per second. The method we used for image processing was called background subtraction. It's a very simple method, but it's also very effective. There's 3 different varieties. We looked at frame difference, approximation of median, and mixture of Gaussians. In that order, they're low complexity up to high complexity, and low computation up to high computation. We chose frame difference because it was easier to use and it gave us adequate results for our purposes. Frame difference. Subject must be identified before we can track it. We use MATLAB to capture the frames from the video and then process them using the processing toolbox. We first take the images and we convert them to grayscale so that we can use them later with certain functions in MATLAB. Otherwise, the functions do not work on them. They need to be in a certain format, and grayscale is the format we need. So frame difference works by taking one frame, taking a second frame, subtracting the second from the first, and then taking the absolute value of that entire matrix of pixels. So that's the equation right there. Take the first frame plus 1, subtract that from the first one, take the absolute value, and that's the new, what we call the targeting matrix. We then compare each pixel in that matrix to a threshold value. If that pixel's value or intensity is larger than the threshold, it depicts movement, because the pixel's value changed a large amount in color. So from one frame to another, it's not the same. Background pixels do not change between consecutive frames. Foreground pixels do change. They have a value larger than the threshold. So, like I just said, the higher the threshold is, the harder it is for a pixel to be foreground pixel. So we had to mess around with the threshold value. So to get the perfect amount, too high, we wouldn't see any foreground. Too low, we would get too much. Foreground background differentiation. I already said that. Foreground pixels are set to value 1 in the matrix, in the FG matrix, which are white pixels. Background pixels are set to 0 or black. The amount value algorithm, like I said, is the frame difference algorithm is executed. Then we use morphological operations on the black and white tracking matrix, such as BW area open with the parameter pixels. When we pass that parameter of pixels to BW area open, it finds blobs of white pixels or foreground pixels with an area equal to or less than the pixel value that we pass to it, and it turns them into background. This truncates a lot of unwanted noise, such as rain, trees waving, things that we aren't interested in tracking. And then we also use infill, which fills in holes of background pixels or black pixels. Say we have like a car we're tracking, the side of a car door is the same color without. So from one frame to another, it's going to have the same color, but it's still technically moving. So this eliminates those background pixels that are going to be seen, since it's the same color from one to another. So it's going to fill those pixels in with white pixels. To identify the target we want to track, we use the command called region props. It returns 3 parameters, which were area, centroid, and bounding box. We parse the areas of each blob found using this command to find the largest, which is our target that we want to track. The centroid of a blob is the center point of the blob, and we'll use that later to track the object as well. So this is a diagram or a video feed or an image of what the targeting matrix would be like after we put the rectangle around for tracking. This is the left side of the camera view and the right side of the camera view. And this white humanoid shape would be, say, our object we're trying to track. And we also place a blue rectangle around it for easy identification. Now, to control the servo to turn the camera towards our object, we have to take some math into account. There's the camera view, which has 2 halves, left and right. And if we divide, since we're using a 640 by 480 matrix, we're using a 640 columns, we divide that by 2, so each half has 320 pixels. So if the centroid of the object we're trying to track is, the column value is larger than 320, it's in the right half. If it's below 320, it's in the left half of the camera view. So then we take serial communication and we send that centroid value to the max32, indicating left or right. And we also calculate the percentage to the right or the left from the origin of the camera, and that's used to calculate the length of rotation of the servo motor. So that we have to tell MATLAB to pause for the same amount of time. Otherwise, we encountered this one problem where the camera was taking pictures during motor rotation. If we don't tell MATLAB to stop during motor rotation, it's going to take pictures. It's going to take one picture, then another picture, subtract them, do the entire frame difference algorithm. And that resulted in a majority of the targeting matrix to have foreground pixels, meaning something was moving. But this wasn't true. It was only seen as moving because the camera was moving while pictures were being taken. So we need to tell, like, do the algorithm, turn, wait for MATLAB, stop, then start taking pictures again. And we figured that out by messing with delay times in MATLAB, and we couldn't really find a perfect number, but we got a good enough one that works. So after the pause finishes for the motor, a new first frame is then taken and the algorithm is repeated. So then the communication between MATLAB and Max32 is essentially, we receive bytes from MATLAB via a serial cable, which is, we use the TTL232R serial cable because between the laptop and the Max32, we need a voltage shunting. The laptop sends out serial communication with a height of 12 volts, while the Max32 can only handle 5 volt communication. So this cable that we purchased takes care of that. PW, the pulse width modulation pin is configured for using the servo motor using a timer, and then we turn the motor in the desired direction as told from MATLAB for the calculated amount of time. So the camera ends up pointing directly or maybe a few pixels off from the centroid of the object we're trying to track.
And here's just some of our engineering constraints. We have
health and safety, which, like I said in the beginning, Our project will allow soldiers at war to be safe when at base or camp, keeping them within the base and not having to be on a turret in harm's way.
Sustainability and tracking system, we wanted to allow the soldiers to do their job effectively, and we want them, if it's installed on like a bank, we want it to conduct their business with minor interruption or worry.
Social and political. A camera with tracking ability will give home and business owners peace of mind so that they don't have to worry about staying at home or leaving the lights on to deter intruders or burglars.
And we also want to give them their home environment to be pressure sure that their product that ensures safety and security. And basically, tracking systems takes a lot of time and effort, and writing code is really frustrating doing this. And senior design is really tough. It takes a long time to get through.
A lot of long hours, a lot of frustration.
We originally were going to take 2 motors, see which one would work for our application, and it turned out like the servo motor worked better for our application.
In conclusion, senior design is very frustrating, but it's also a great learning experience, and we learned a lot doing this project, more than I thought we would. So we would like to thank our professors and our fellow peers. I'd like to thank my mother for not disowning me for coming home after 1:30 numerous nights.
And caffeine.
Not telling her.
Also.
Especially caffeine. And very much thanks to Dr. Vaziri for being our advisor and helping us when we needed it.
And here are our references.